Good evening. Welcome to this program, My Teacher, the biggest classroom of the UAE. So, the last week, some of you might have been in the busy preparation for the examinations, and by now, I hope most of the schools, the examinations or FAs might have got over. Now, you must be in a serious mood of packing up and getting ready for enjoying the vacation. And of course, in senior classes, students, you may be in a plan. Sometimes you may be going to India, or sometimes you may be going to stay here itself. Busy with some preparations for the ones which got over. So, of course, a basic thing I want to tell you is, you analyze yourself what all you have missed in the first term, contents, or what all you found difficulties in the first term. So, definitely you sort them out and try to rectify them very fast or as early as possible. But before that, you have to see where all the materials, notes, textbooks, everything it's there with you. And if you could get the past papers or the board examinations, it must be in a if the board papers or the guides you should have with you, and keep practicing questions as many as possible from the sources whatever you have. Anyway, I want to inform something to you. Vacation is going to begin after 26th in most of the schools, whereas after the vacation, when you come back, you be prepared and make sure that you have revised the contents very well. And this program, we are going to have a pause for today. After today's session, we will be able to meet again only after the vacation. So, by then you may keep collecting your confusions, doubts and all, keep them ready. We will be right back after the vacation. But anyway, today my focus is for grade 12 students, some contents of physics, the chapter Electromagnetic Induction. Some part of the electromagnetic induction you have already done. Deepthi ma'am already explained all the concepts related to basic concepts related to electromagnetic induction. Today I thought of winding up the chapter with the remaining contents as well, to discuss the remaining contents as well. So, some areas like self induction, mutual induction, application, all those things we will be able to explain today. So, for today's session, again let me tell you, my dear students who are doing in grade 12, who are studying in grade 12 science stream, we are going to discuss contents of physics, the chapter Electromagnetic Induction. Electromagnetic Induction. Okay, certain areas, because almost half the way it's over. Okay, the last sessions we have done that. So, remaining we will do today. All right, let's get into the concepts. Very first thing is basics of electromagnetic induction. What is electromagnetic induction? And there are two basic laws related to electromagnetic induction. Just to recap. So, very basic thing to understand is, you must have seen the cycle dynamos, the bicycle dynamo. That is one of the examples where you can make out that electromagnetic induction is made use of. Electromagnetic induction basically, it's something to say about production of electricity. Electricity, to produce electricity is something great, because we need electricity for different purposes. You are familiar with AC generator, DC generator and all. They are all producing electricity. Production of electricity is what is done by the phenomenon called electromagnetic induction. So, electromagnetic induction, from that name, the name itself gives you one picture. Electromagnetic induction means we are producing, inducing electricity. So, you might have seen this, you can see on the screen, you can see one picture. This is a magnet. When the magnet is coming close to it, you see it's coming close to the coil. Now, you know, when the magnet is moving, you can see the bulb is glowing. You might have seen that. See, when it is coming close to it, the bulb is glowing brighter. And if I am moving slowly, the bulb is not glowing that much bright. But if it is moved fast, it is glowing very bright. You know, what does it mean? See, if it is at rest, there is no current. If it is moving slowly, very less current. Say I am keeping it inside, see, there is no current. But if you move it inside, lots of current is produced. Otherwise, large amount of current is produced due to the quick movement of the magnet. So, there is a magnet, you can see the magnetic field lines are there. See, there are magnetic field lines. So, when you are moving this magnet towards the coil, what happens is these magnetic field lines are being cut by the coil. The cutting of the magnetic field lines, otherwise changing of the magnetic field lines, is what is leading to the phenomenon called electromagnetic induction. That is the concept of electromagnetic induction. So, what do you understand from this is the electromagnetic induction phenomenon shows that the example which I showed you, the demonstration which I showed you, it is like what we observed is the greater the movement, you know, the faster you move, the greater is the amount of current produced. So, current more if change is more. So, this is what is the concept of Faraday's law. Faraday's law says the rate of change of magnetic flux is what is nothing but the EMF induced. So, one equation we have seen there is E is equal to minus d phi b or d phi by dt. This is one equation you have seen. This is one basic equation where phi is the magnetic flux. You know what is the equation for magnetic flux? Phi is equal to BA cos theta. Alright. So, from this only we make out one thing. If you change the magnetic, see from the equation we can make out that what does, by the way, what does the negative sign indicate? Negative sign shows that the change in the flux is opposed by the induced EMF. Otherwise, induced EMF opposes the change in flux. This is very much required to explain the second law, what you call as Lenz's law. So, that is, so this is Faraday's law, and Lenz's law says another concept, you know, that is when this negative sign, the EMF induced always opposes the change in flux. This is what is Lenz's law. Okay, so let me ask you one thing. You know, you might be familiar with the bicycle dynamos. When you are cycling the when you are cycling a bicycle, when you are riding a bicycle, there is a dynamo. The dynamo which is, you know, kept along with the rear wheel, that also moves. There is a magnet inside. So, when it is moving, the magnet, the coil is moving around the magnet. So, I will show you a demonstration on that. I will show you after some time. But there one point you have to understand is, just think of the case when you use when you are cycling in two situations. One is with the dynamo off and with the dynamo on. If you are keeping the dynamo on and cycling, what happens is you will have to apply more force, or you will have to do more effort, you will have to do more work to cycle. Why? Because some amount of energy is used up to rotate the dynamo, that is getting converted into electricity. That electricity is used by the headlight. So, light up the headlight, we are taking the electricity produced by the dynamo or in the dynamo. So, there what you have to understand is, when you are cycling, we are spending energy, otherwise we are doing work, and some work is required for cycling, but in addition to that, some amount of energy extra required while cycling if the dynamo is on. That is what is used up to convert, you know, that energy is getting converted into electrical energy. So, this is what we say, that means the current so produced by the change of flux opposes the change. That is why we have to do work. No, doing work, whenever an opposition comes, you have to do work. So, in this case also there is an opposition. This opposition is what is causing or what is leading us to do work. That is why we are spending energy. This energy is only converted into electrical energy. Otherwise, we can say all of a sudden how the electrical energy coming from, or where the electrical energy coming from. It's according to law of conservation of energy, energy should be it should not be created, it should be converted only from one point to the other, one form to the other. So here what energy conversion is, what's happening is when you are moving the dynamo or when you are moving a magnet, we are spending some energy, there is mechanical energy spent, which is getting converted into electrical energy. So the Lenz's law is very well explaining the verification of the law of conservation of energy. Okay, so we see that by electromagnetic induction electrical energy is produced, but in fact it is not really produced, instead it is getting converted from the mechanical energy which we spend to electrical energy. So there is a very important question there, that is we have to state the law, Lenz's law, that is, this is the question, state Lenz's law and explain how Lenz's law is obeying law of conservation of energy, or it is in accordance with the law of conservation of energy. Okay, is that clear? So once again I will explain the answer to that. Lenz's law states that the EMF induced opposes a change in flux, and this, to explain that, we have to explain using the movement of the case of, that is what is explained in the last session. So that is when a magnet is pushed into the coil or taking out and all, there is always an opposition against which we are doing work, due to which we are spending energy. This energy is getting converted into electrical energy, so energy is not anywhere coming from anywhere else, okay, from us. So while cycling, therefore the energy is, electrical energy is produced from our body only, we are only producing electrical energy. Is it clear? Alright. So that is one concept about electromagnetic induction. Then another aspect I want to explain to you is that, you can see, now you look at the screen. So you can make out one thing, there is a bar magnet. I will show you a few things related to electromagnetic induction. A bar magnet, you can see the bar magnetic field lines are what is indicated there, you can make out clearly. Okay. Then this is the case of a magnetic field line around a bar magnet. Then you see there is a coil. This is what is indicating the phenomenon of electromagnetic induction. See, when the magnet is moving close to it, so you can see the bulb is glowing. So if it is large change means bulb glows brighter. This is greater the rate of change of flux, the greater is the current produced, greater is the EMF, otherwise greater is the current produced. See, this is what's the phenomenon, what you call as electromagnetic induction. See, like this also, either way. Okay, but this is moving faster means large amount of current, but if you keep it inside, it is at rest, no change means no EMF, no current produced. So this is what is showing the phenomenon of electromagnetic induction. And an electromagnet is what is shown over here. There again you can make out one thing. See, if I am keeping the voltage 0, no current means no magnetic field. So if the voltage is developed over here, or if the battery is connected to it, there is a current flowing, due to which there is a magnetic field produced. So there also we can see the magnetic field lines. Alright, then another one is this generator. How electrical energy is produced. This the AC generator is what is explained in the last class. See, I can show you one thing. You must be familiar with the hydroelectric power stations. This is what is basically happening. See, this is the water is flowing. You can make out one thing. If very less amount of water flowing down means very small amount of electrical energy is produced. See, the change is very less. But if the rate of flow of water is increased, so large amount of water is flowing, you can make out one thing. Okay, large amount of water is flowing means there is a greater amount of energy is getting transferred. That is why the mechanical energy to rotate the magnet is increasing, thereby electrical energy produced also is increasing. Okay, this is one thing you can make out. See, large amount of water falling down. See, this is what is basically the principle of hydroelectric power stations. So I showed you the case of bar magnet, the pickup coil, that is to indicate the electromagnetic induction phenomenon, and how the electromagnetic field or field of electromagnet. Then I showed you about a generator as well. The another aspect I have is about transformer, that I will explain to you after some time. So now I will show you the very basics of this session, this chapter rather. Alright, you can look at the screen again. So first I explained about Faraday's law of electromagnetic induction, the equation d phi b stands for magnetic flux. Then we have, this is what I explained. You look at the diagram carefully, the bicycle dynamo, how it functions. Okay, while rotating, the magnetic field is changing. When magnetic field is changing, current is being induced over there, electromagnetic induction happens over there, and that is what is carried away to the headlight. So, it produces electrical energy and converting into light. Okay, so, this is the working of AC generator, which you have done already. AC generator, this figure is important, and this is the second diagram, that is the graph, that is what is indicating how the EMF is varying with time. So, that is why this is called alternating current. You can see it changes from positive to negative continuously, right. So, now I will explain concept called self induction. Now, listen here. Okay. Now, look, self induction. All right. So, this self induction, to understand what self induction is, you may recall one thing which you studied in grade 11, that is electrical inertia, inertia, because over here the self induction is also termed as electrical inertia. First, what do you mean by inertia? You studied in 11th grade. What is inertia? Inertia is something like, inability, or otherwise we can say ability to oppose the change to a state of rest or of uniform motion in a straight line. A body at rest will tend to remain at rest only. Okay, it always opposes a change. If you want to change the state of rest, or if you want to change the uniform motion in a straight line, we will have to apply force. Why we need to apply force? Because the system opposes us. It does not want to change. So, we have to make it change. The change to be made, for which we have to apply a force. So, the ability of a body to, or the property of a body to oppose any change in the state of rest or of uniform motion is what is termed as inertia. Same way, over here you just imagine, just one example I will tell you first to understand about self induction. There is an AC circuit, alternating current circuit. Okay, the normal circuit that we use in household is what is AC circuit, alternating current circuits. A bulb is glowing, okay, in the alternating current circuit. Imagine you just connect a copper coil, like a solenoid. You just connect a copper coil. Copper coil means, why I am using copper is because its resistance is very, very low. There is practically there is no opposition to the flow of current, let us say. So, the coil you connect in the electrical circuit in which a bulb is glowing. So, what will you observe over there is, the moment you connect the copper coil there, you may observe the bulb may become dim. The brightness of the bulb can reduce. That is, just by connecting a copper solenoid or a copper coil of sufficient number of turns in an AC circuit, the bulb will become dim. Think on that. Why it happens so? Why the bulb becomes dim when such a coil is connected? We can make out this way. Just now we discussed the case of electromagnetic induction. When you connect a coil like that, a copper coil when you are connecting, there produces a magnetic field. What kind of circuit we are using is alternating current circuits. What is the peculiarity of alternating current circuit? The current keeps on changing, keeps on fluctuating. The direction and magnitude both will continuously changing. Right. So, due to which, if current is changing, what else is happening? The magnetic field around the circuit also is changing. So, there is a changing magnetic field in the circuit itself. In that only we are connecting a copper coil or solenoid. Then what happens is, the solenoid when carries current produces a magnetic field. That magnetic field is continuously changing. Why? Because it is alternating current. According to Lenz's law, very first according to Faraday's law, it will induce an EMF, right. So, within the solenoid an EMF will be induced, but by Lenz's law we say that this induced EMF opposes the cause. Here what is the cause? The alternating current, changing of current is the cause. So, the current flow is the cause. So, what will happen? The induced EMF so developed in the solenoid will oppose the flow of current in the circuit, right. According to Lenz's law, it opposes the cause, it opposes the flow of current. So what happens? The induced EMF so developed in the solenoid will oppose the flow of current in the circuit, thereby the total current in the circuit will reduce. Alright. So there is an EMF induced within the coil itself, that is called self-induction. Inducing EMF in a coil due to the change in flux developed within the same coil itself. So in that case, you at this point of time you may think in this way, that is normally in DC circuits, how do you reduce current in DC circuits normally? That is what you studied in current electricity lesson and all, we have seen that. How do you reduce current in normal circuits? By connecting a resistor. But when you connect a resistor, what happens is there will be physical opposition to the flow of current. When electrons are coming like this, it will be physically opposed. So what happens? A lot of energy will be wasted there. It will be converted into heat. So current is reduced, but by the expense of some energy. But over here what is happening, when such a solenoid is connected in a circuit similar to what is AC circuit where the current is fluctuating, there without opposing or without causing a loss of energy, current is reduced. This is what exactly is required. So in AC circuits, therefore, instead of resistor, what you can use is we can use such a coil. We call such a coil as an inductor. Resistor is this one. Now we have a component called inductor. This is inductor. This is a symbol of inductor. So in an inductor, there is self-induction happening. So what is self-induction? Phenomenon of inducing EMF in a coil due to the change in flux developed within the same coil itself. Alright, this is the self-induction, and such a coil can be used in AC circuits to reduce current in the circuit without significant loss of energy. This is important. Alright, when you use such a coil there or such a solenoid there for opposing the flow of current, we call it as an inductor. Okay, resistor, inductor. So there may be a question like, why do we prefer inductor in AC circuits rather than resistor? Reason is clear. Resistor, both will reduce current, but resistor causes loss of energy in the form of heat, right? Here there is no loss of energy. So we can say inductor causes what kind of opposition? A non-resistive opposition. Non-resistive opposition is caused by inductor. The other one is physical opposition to the flow of current. That is the difference. Alright. Now there are some quantities related to this. Self-induction when happens, just think of a coil like this. It's a coil. When current passes through it, how many turns are present over there? Accordingly, total flux will be developed. Okay. So phi is, if I say phi is the magnetic flux, we can say it is proportional to the current. The more the current passing through it, more is the magnetic flux. Okay. So here we can say how much is the magnetic flux developed by in the coil or in the solenoid. That depends on obviously current. Now what other factors? Other factors are depending upon the coil. How many turns, what's the nature of the medium, right? And even the area, all these factors are there. All together coming into a single quantity that is represented by a constant L, right, I. This L is what is called coefficient of self-induction, or we can also call it as self-inductance of the coil. Self-inductance of the coil is L. So one thing we can clearly make out, so, you are familiar with resistor. Now we have seen inductor. Resistor has resistance represented by R. Same way we can say inductor has inductance represented by the letter L. Alright. And also we have seen a similar equation in current electricity lesson. We will just compare and see. We know V proportional to I, or V is equal to IR. So instead of V is equal to IR, here we have phi is equal to Li. Here R is resistance. Resistance is V by I. Similarly, we can say L is phi by I, magnetic flux by current. This phi, unit of magnetic flux, it is Weber, and unit of current is ampere. Weber per ampere is replaced by a single name that is called Henry, represented by the letter H. So Henry is the SI unit of self-inductance. So inductance SI unit is Henry. So we may define 1 Henry as the magnetic flux per unit current. phi by I. This is Henry. Is it clear? See, this is Henry. Similarly, for resistance we have the unit ohm. Ohm, the unit of this is Henry. All right. Now, we know in resistor, they will compare with that. In resistor, we have seen resistance of a wire, that is depending upon what all factors. We know the equation rho L by A. That means resistance depends on the nature of the material, temperature, the length and area of cross section. Right? We have seen, we have discussed this one in one of the previous sessions. So, similarly, so we have equation R is equal to rho L by A. Similarly, we can have an equation for L as well. Right? So, what will be the equation for L? What are the factors on which the self inductance of a coil or inductor depends? Right? One thing already we know is resistance depends on these factors. Similar to this, we have an equation for this. How do you get it? Listen, it is in fact an important derivation question. A coil having n turns and length is L, right? We know magnetic flux is directly proportional to current, or we get an equation phi is equal to Li. This is one equation we have seen. And we have another equation for magnetic flux in general. I just mentioned about this equation at the beginning of today's class. Phi is equal to what? Ba cos theta. If there are n turns, we may even write Nba cos theta. Right? This is another way. This is one way of writing flux. Another way of writing flux is like this. But you know, it has got n turns. All right, n. How about B? B, equation for magnetic field inside a solenoid. We are familiar with the equation mu 0 n I. That's the equation for magnetic field inside a solenoid. Into A, cos theta. Theta is the angle between the area vector and the magnetic field. You know, the magnetic field due to a solenoid is like this. That way itself, you know, the coil, plane of the coil is like this. Right. So, the area vector also comes in this way. So, area vector and magnetic field vector in the same direction. So, theta is 0, cos 0 is 1. Okay. So, cos 0 is 1. By the way, this n, capital N, can also be written in another way. See, what is this small letter n? N is the number of turns per unit length. See, like this you can write. So, we may replace capital N with what? Small n into L. So, n L multiplied by mu 0 n I A. So, what do we get here? Mu 0 n squared A L I. This is one way of getting equation for magnetic flux. So, we have an equation magnetic flux phi is equal to Li. We have the equation for magnetic flux here this way as well. So, just you compare the first and second equations. This gives, what do you get from by comparing these two equations? We see that the self inductance of the coil L is equal to mu 0 n squared A L. This is the equation we have derivation from this. This is a case of self inductance. All right. So, self induction, phenomenon of inducing. Have a look at the screen. Self induction, it is a phenomenon of inducing EMF in a coil whenever it has a change in magnetic flux linked with it. It is also called electrical inertia. This is what I said, you know, opposition to a change. This is what I just mentioned about, you know, what you studied in 11th grade, inertia, opposition to change of the movement or change of rest. Okay. But same way, here also it is called electrical inertia because, why it is called electrical inertia? Because whenever there is an whenever there is an EMF induced, it is opposing the change. Whenever opposition of change, okay, then we use the term inertia. That is why this self induction is also called electrical inertia. Anyway, we just mentioned about self induction. So, we will discuss more about the self induction and a device related to this after a short break. After the break, when we come back, we will discuss more contents related to this. So, stay tuned, we will come back after a short break.